Okay, so we'll be doing that Atcoder beginner round 466. And I'm going to turn off the AI. Okay, so let's start with D. So there's a grid of n rows and n columns. Initially nothing is placed in the grid. Starting from this state, he performs m operations in the grid. The ith operation is as follows. Remove all pieces placed in the row Ri. Next, remove all pieces from the Ci. Finally, place a piece, cell Ci and Ri. After the m operations, okay. So we have okay, num pieces of row counts of I equal to 0. Call count. Okay, this is n times m. N times m. So every row and every column has exactly 0 entries. Okay, that is also then we have this, or we also have okay, we do m operations, n rows and n columns, sorry. We do m operations or comma c int total pieces equal to 0 if pieces total pieces minus equal to row counts of R plus call counts of C. If pieces dot find of R comma C not equal to pieces dot end total pieces plus plus inclusion exclusion, then you do row counts of R equal to call counts of C equal to 0, and pieces dot insert of R comma C total pieces. Hold on. So you remove both of them. Yeah. Then you need to add this. Okay, so row counts for equal to call counts of C. 2, 1. I think finally this is what's happening. Okay. We need to remove all the pieces. Not equal to row counts of r dot end. Yeah, removing it twice. Insert of c. Call counts of c dot insert of r. Yeah. Row pieces and call pieces. Call pieces. One, two. Two. That doesn't make sense. Oh wow. going to be 1 1, then 1 2. Okay, it's not right. 2. Yeah, this should work, but might TLE. Let me check. So for each row pieces, we're going to remove it. Yeah. Let's say we just keep adding to the same row. Very sparse. That might not. Okay, it's worked. Okay, range flip. So the end cards lined up. The front side is AI and the back side is BI. You can perform the following operations at most key times. Choose an integer L and R satisfying. For each integer I satisfying this, flip the card I. Here, flipping of a card means find the maximum possible value, the sum of the numbers written. You're going to flip. Oh, doing a range flip. Yeah, if you're doing a range flip, it's best to be disjoint, because otherwise you can just undo the flips. You can do exactly K flips. It should be some kind of dynamic programming. Most K flips. So let's say so dp of I j max, you got exactly j flips 1 to I, right? Okay, j goes from 0 plus plus. So obviously if you did 0 flips, yeah, so dp of ij is the same of dp of ij minus 1. It's the sum of them, right? Flipping of the card means this, which means int you cannot do any flip. That's fine. To kj plus plus dp of dp of 0 j is equal to 0. Or we can do, maximum minus inf, let's call it p of 0 0 equal to 0, because that's not possible. Once we do this for int, so it's the most brute force way to do it. So so let's say the last card is flipped most k times. If the last card is flipped, dp of ij is equal to max of dp of ij, comma, so it's the sum from I to I. So that's going to be the difference diff of I minus diff of I, or we call it as prefix sum of I minus prefix sum of I minus 1 plus dp of minus 1 j minus 1. Okay, if j equal to 0, obviously continue. Plus you did not flip, so it's just going to be a of I. So then we can do prefix underscore sum of 0 equal to 0. Prefix underscore sum of I is equal to prefix underscore sum of I minus 1 plus a of I minus b of I. ll prefix underscore sum max n plus 2 hash define max n's 2 1 2 3 4 5. So that's your dp. So we have ll of dp of max n plus 2 max k plus 2, and then we have hash define max k is 10. So we have all of these, and then finally ll ans equal to say minus inf for int j goes from 0 j less than equal to kj plus plus ans equal to max of ans comma dp of n j. So first let's check the correctness of this, then we optimize. So a of I we don't need, I think we just need b minus b, or we can just do b minus a of I, because that's what we get when we flip it. You don't flip it. No, it's I minus 1. So prefix sum of I, so you flip it, then you don't, and then from I minus 1 onwards, this is the amount you get from flipping from I to I. In I minus 1, no, that's not right. So we need b minus a of I. No, this is just B, obviously. If you flip it, this is you don't. Yeah, that's right. Let's check the correctness again. 35, and what is this? 47. Yeah, so now it's correct, but it's too inefficient. So all we have to do now is, so we have find the max II such, so dp of I minus 1 j minus 1 minus prefix sum I minus 1 is maximized. Need to find that. So for a given j minus 1, for int j goes from 0 j less than k j plus plus, dp of I minus 1 j minus prefix, this goes sum of I minus 1. So add this to the maximum. Okay, mx of j is equal to max of mx of j, comma this thing, right? So we start off with mx of j minus inf. So mx of j is minus inf. Then we do basically dp of ij is equal to max of dp of ij, comma prefix sum of I, which is a constant for I, plus mx of j minus 1. We can remove this. Max k plus 2 plus 2, yeah. It's 47, then 35, then 45. That should work. Yeah, that should going to be efficient. Okay, so many mod calculations. So given it integers x, n and x. First, let's see how many people solved f. Okay, quite a few. Okay, so given integers n and x, then length n sequence of positive integers. For a non-negative x, define f of x is. Find the number of integers x between 1 and x. Includes this is that f of x equal to 0. Okay. F of x equal to 0. So recursively take the modulo. Then at some point it has to hit 0. Okay, so this one. So we need this somehow. A of phi. So A of n, the last number. Zero times k. It's modulo n minus 1. Yeah, q of n plus r of n. So last number is obviously this. That's the output of A of n. That comes before this. So we have x, whatever, what, so x percent A of n minus 1 is equal to A of n times q of n. So which means x is actually A of n minus 1 times m plus A of n times q of n. Yeah, that's right. And what else? So y is equal to p of n minus 2 times, so that's going to be your x. So y must be, so whatever y percent A of n minus 2 equal to this, which means y is actually m prime times A of n minus 2 plus this. Okay, so we'll say z percent A of n minus 3 equal to this. Okay, so it is just take the modulo. is a linear combination of all the numbers. Between 1 and x. Okay, so let's see. It's 1 0 0. Yeah, 0 0 1. There is also between 1 and 7. What about 7? If it is 5, it will work. 2, it will work. 3, it will work. Okay, because 2 plus 3 is 5, so it's redundant. Anything that can be expressed as a linear combination of these numbers. But 1 cannot be expressed. Four can be expressed. Six. Let's get back to this later. Maximum size ball of color K. Now to judge the following questions. Choose integers I and j and ask whether the distance of the point is at most 1. But the number of pairs is distance is at most 1. Most 2n times. It's easy. So j equal to minus 1 or 0. Number of pairs of integers, most 1. Okay, they're just like real numbers. Come on. You just asked this. So instead of like doing this a flash of std out, int so while j plus 1 less than or equal to n, and then ask of I comma j plus 1 is equal to 1. X of I comma j plus plus, then from I to j everything, number of pairs of integers, I to j minus I. Cout ends. No, so finally we just need to, once you have found the answer, exclamation %t, you flush from std out. Three is given. 3 is 1. So, okay, you just get yes or no. String ends in if return and is equal to yes. 3 yes. So 1 3 no. 2 3 yes. Yeah. Should work. Now let's go back to that problem. 71 solvers. Okay, so integers n and x. Yeah. So if we go backwards, let's just go backwards. So the last element needs to be a of n times q of n. That's fine. Second last is x. And the last just before the last. So second last. Let's just before the second last. There's that x% n minus 1, so a of n times q of n. So this means this whole thing must be less than n minus 1 obviously, or q of n should be less than or equal to a of minus 1 divided by a of n. It has to be. That's for sure. So which means x is equal to q of n minus 1 times a of n minus 1 plus a of n times q of n. Is that right? It has to be q of n minus 1 times a of n minus 1. Yeah, that's right. But q of n is less than or equal to this. So that's your x. So now if you go back, x percent a of, so let's call it as x second last input of n minus 1. It's called the input of n minus 1. So input of n minus 1 must be this. Finally, we have input of n minus 2 percent a of n minus 2 should be equal to, yeah, that's essentially this input of n minus 1. That is this, which means this whole thing must obviously be less than or equal to a of n minus 2 minus 1. Right? So from this we get one more condition. Then the input of n minus 2 is actually q of n minus 2 times a of n minus 2. Yeah, a of n minus 2 plus this. Okay, so generally put, so we always need, that is your input of n minus 1. So we always need input of I is less than or equal to input of I always less than or equal to a of n, because that is actually coming out of the previous one, right? And we also have input of I is equal to sum of j goes from I to n a of j times q of j. That's there. Shit, so hard. Okay, so this thing So input of I is most a of I minus 1. Input of I. So input of 1 is x, the original x. So input of I goes to a of I. Yeah. How do we optimize this? Yeah, if it's a linear combination. Okay, I see. So Q of G is less than or equal to because that's the remainder. Extremely hard. That's what we want. Let's say I have this constraint. Can be all zeros. Wow. So it's 100. 97 and say 93. We have the set of all numbers. Yeah, that 500. Who's calling? 1 to x. Each range otherwise 0 to a minus 1. Then sum max. Percent a l and x percent a 0 to a minus 1. Question is go back of a minus 1. X is greater than or equal to a. Full ranges. X minus a. Divided by a. That makes sense. So x minus a if x is 2 times a minus 1. The full range is 0 to a minus 1. Here. Divided by a. You underscore ranges. Okay. Maybe just do this map. Ranges of x equal to 1 ranges. New underscore ranges of x. Yeah, new underscore ranges. Auto x equal to ct. Continue. So x is greater than or equal to a. You obviously need new ranges of a minus 1 plus plus, that's there. Then we also need the full ranges. Yeah, the full ranges of this. A minus 1 plus is equal to num full ranges. It's your R. R plus 1 to a minus 1. No, actually 0 to R. It's your remainder. So it's the full ranges. So if 2a minus 1, for example, right, then R is equal to a minus 1. I think it should be R plus 1. Let's do it carefully. So essentially we have x is greater than or equal to a. So we have 0 to a minus 1 is 1 per chunk. Let's say 2 times a minus 1. Then we have a to 2 times a minus 1 is another chunk. So full chunk. So if it's 2, so if x is equal to 2 times a, then it's going to 0 comma a minus 1, a comma 2 times a minus 1. Then we have a single 0. It's your remainder. If r plus 1% a is not equal to 0, right? Equal to 0. If R is A minus 1, that's what it means. 0 to R. Yeah. R plus plus. That's right. Then swap of ranges, new ranges. Then finally, we need to have ranges dot size. Why? Because minus 1. So at the end of it, what do we have? Oh, God. Yeah. So it's a 7 1. What is this? 2 1 4 1 0 2 1 3. Two. No, not like that. Plus equal to CT. New ranges, that's not right. That's right. That's right. Okay, so now it's not going to work. BTL. I think that's an easier way. So these are the ranges, right? So what you do is file 1. Need to find auto IT ranges dot lower underscore bound of needs to be at least a comma minus 1. Residual IT first, LCT is 90 second. Okay, ranges dot arrays of IT. Don't need this. Lower bound of A. While if IT ranges dot m break. Yeah, maybe that will work. It's a TLE. That's great. So this might work. Okay. Okay, this worked. Nice. That was hard. Yeah, so okay, so F is an F. So all we have to do is, so first you have all the numbers from 1 to x. You call it from 0 to x, right? So what you're doing is every time we get a number A, right? Obviously anything that's less than A does not get affected. Anything that is greater than or equal to A, so it gets broken down because into multiple chunks. So let's say it is 0 to x, right? So those are all the numbers from 0 to x. Obviously the 0 to A minus 1 stays the same, and that's why we get this, right? We increase the ranges of A minus 1. From A to x, we are basically breaking it down into multiple pieces. So if x is, for example, t times A minus 1 for some t. So you first take the remainder, right? So the number of full chunks in this case, it's going to be x plus 1 divided by A. That's the number of full chunks. So x plus 1 so from A to x, right? Essentially if it's this to t minus 1, so the number of full chunks in this case, it's t minus 1, right? So which is just x plus 1 by A minus 1. It's the number of full chunks. Actually I added this as well, so you can as well just do x plus 1 by A. You can remove this, so x minus 1 by A should be the same. Yeah, 3491. No. Yeah, so the number of full ranges minus 1. Anyway, so this is more easier to understand. Something has changed. One second. Yeah, that's fine. just to x plus 1 by n can remove this. That's what I meant. Yeah, that's right. Yeah, x plus 1 by n, remove this. So the number of full ranges is 0, 2. So let's say it's x, right? And if x equal to t times a minus 1, then it's just x plus, then it is t. F, so it's just x plus 1 divided by a is the full ranges of a 0 to a minus 1, a minus 1 to add. Then there is a remainder r. So obviously if the remainder is a minus 1, it is already, last one is already a full range. Otherwise you need to add 0 to r, and that's what we are adding here. So it's essentially each segment of numbers gets broken down to multiple pieces. That should be the simpler solution. We don't need this new ranges. So all we are doing is just updating the ranges in place, finding the smallest value which is greater than or equal to a, right? Because anything less than a does not get affected. Anything that's greater than a gets broken down into x plus 1 by a full ranges, and then the final remainder r gets a ct, and ct is this count here. Okay. This should be more simpler to understand. Great. Okay, I don't think I'll be able to solve this. Oh, that was a nice one.